We are on. Great. Where did we start? We started using the standard Schrodinger equation. We applied we used the potential, the harmonic potential. We substituted that and we simplified that equation, remember? And we arrived at an equation which is d square u by, no, d square psi by du square plus lambda minus u square psi equal to 0. Okay, this is easily solved. Okay, where lambda is 2e by h cross omega, and there is also one more constant which is alpha x, and alpha is actually determined. The alpha has a particular number for that. You just please check the lecture note. There's a particular form for this alpha. Okay, and if you follow the equation number 1 and follow that substitution, you'll actually get to know what is alpha. Okay, it's not a series of numbers, it's just a proportionality constant, and you have some number which is in terms of the mass of the oscillator. Okay, I think it has to have a square root of mass. Now, as I said, this equation can be solved, and the general solution for this is in terms of the wave function. And we wrote this function as psi of u as a constant times exponential minus u square by 2 plus b times e power plus u square by 2. Okay, that's the general form. While, as I said, for large value of u, this equation comes into picture. I neglected this lambda because I assumed the solution for this equation for large u. Large u means large amplitude. Okay, so in that case, in that simplification, you will get this equation. And if you see that in any of the harmonic oscillator problem, the amplitude, for example, however large it is, this system is confined to small space. Okay, that means the wave function has to be defined at a very, very small space, whatever the amplitude it is. The amplitude cannot be like 1 mile, right? It is just hardly 1 angstrom units or few nanometers. Okay, so that means this function is only defined at that small amplitude, even though we say that it is for the large value of u, but it is actually a very, very small amplitude. Okay, so that means this function is very local. Okay, very local means the function goes to 0 as x tends to infinity. So this means that the psi of u should go to 0 as u goes to plus or minus infinity. This is our assumption, that you have a system which is allowed to oscillate at its equilibrium position. That means however large amplitude I consider, but it is still local. Okay, so that means this function should be a non-zero quantity only at a very, very small value of u or value of x. Okay, so then what happens if you increase the amplitude? If you increase the amplitude, your system is a system which has a spring loaded with a mass. Okay, this can be a iron ball connected to a spring, classical harmonic oscillator. It can be hydrogen atom adsorbed on a silicon surface. The hydrogen atom adsorbed on a silicon surface can also be modeled like this, and it oscillates across its equilibrium position. So you can approximate that for a harmonic oscillator. Okay, still u large corresponds to a confined system, but I consider the amplitude of oscillation fairly large. Okay? Now, as you increase this term actually diverges. It's a positive quantity, and as you increase u, e power u square is really faster increasing. So the only way you can have a meaningful solution that psi goes to 0 as u increases is to consider b equal to 0. Okay? If you do not consider this, you get a meaningless solution, because as you increase the psi or as you increase the amplitude of the oscillation, this diverges, while your harmonic oscillator is really local. The psi diverges means psi is everywhere. Psi everywhere means the square of the psi is the probability of finding that particle. You cannot have the psi at wherever possible u values. Okay, so that is why I consider b is 0. So the resultant function for this oscillator, okay, u is a times e power minus u square by 2. This is my general solution for the harmonic oscillator. I'll write down this again. Psi of u is a times e power minus u square by 2, under the assumption that this u is very large. Okay, so for very large u corresponds to x also. Okay, it's amplitude of oscillation. If you want to call this as a general solution, for example, for an harmonic oscillator, that should satisfy even the smaller amplitude also, right? If I have to call, or if I want to call this psi in this form for any value of x or any value of u, that means this has to satisfy even for smaller value of u also, right? Now here is the problem. You have a constant, it can be a complex quantity. This is the functional dependence, and I get this form only when I assume that the u is large. Okay, so I think we are back on. Okay, so then how to come over this problem? What we generally write is that this A is written in the form of a series solution. Okay, and this series has a term which is a1u plus a2u square plus a3u power 3, etc. Okay, with a general term as aj times u power j. If you just consider this as a constant here, then this solution is valid only for large amplitude of oscillations. But I want to have a general solution which is valid for all the amplitudes of oscillation. So one way to do is write down this constant prefactor in terms of a series, and then try to find out what sort of form this A has so that it satisfies all u. Okay, satisfies all the u values or x values. Okay, and in the lecture note I have substituted this one here, and we solved it, and ultimately you will get a solution in the form as uh, you can go through this and you will get something like this. These coefficients have to satisfy some rule like this. Aj plus 2, j plus 2 is the next term here. It should satisfy 2j plus 1 minus lambda divided by j plus 2 times j plus 1 and aj, of course. Okay, you just go through these solutions here and substitute this. See, what you do basically is substitute this series in this function. Okay, and then find the first order differential, find the second order differential, and substitute here and equate to 0, and you will get into this relation. So the coefficients have to have this kind of relation in order to satisfy this psi of u to be a solution for all the amplitudes. Okay? So where j can take values of 0, 1, 2, etc., etc. Okay? So aj plus 2 is, oops, aj plus 2 is given by 2j plus 1 minus lambda divided by j plus 2 divided by j plus 1 times aj. What does this tell you? For all j, okay? For all j means j equal to 0, 1, 2, etc. Just start substituting 0 value, for example. J equal to 0. What do you get? A2 is j0, so it is 1 minus lambda divided by, this is 0 plus 2, 2 times 1 is 2, aha, great, times A0. Okay, so this gives you 1 minus lambda times 2. That means if you give me the value of j, that means if you give me a value of A0, I can directly calculate what is A2 in this series. Remember, lambda is 2e divided by h cross omega. Remember, okay? 2e divided by h cross omega. So that's a constant. This is also energy, this is also energy. So it's a numerical constant. So this tells you that if you are given with the value of A0, you can immediately calculate the higher even number. So once you calculate E2, you can again, E2 corresponds to j equal to 2. Then you can calculate A4, you can calculate A6 like that. So that means if you are given with A0, implies you will actually get a series of A2, A4, A6, etc., etc. So in that series, for example, I write the series A as A0 plus A1U plus A2U square plus etc., etc. You write the general term here, Aj times U bar j. If I am given with this number, that means I can calculate all these even numbers here. Even numbers I can substitute here and I can get the wave functions. If you substitute j equal to 1, for example, so this is for j equal to 0, okay? If j equal to 1, what happens? It will be 1 plus 2 is 3, so this will be 3 minus lambda divided by, this is 3 times 2, 6, it's a class 2 product or second grade multiplication, okay. So it is 1 plus 2 is 3, 3 times 2 is 6 times A1. So this is for j equal to 1. So that means if you give me the A1 value, I don't need anything from you after this, because from this I can calculate what is A3. If you have A3, then you can substitute again, you'll get A5, you'll get A6, A7, etc., etc. So that means from A1, you can actually calculate A3, A5, A7, etc., etc. Right? So that means once you are given with this j value, which are only 0 and 1s, you can calculate all the functions, series of functions available for all the values of u. Okay, whatever the energy you can consider. So this is my energy, this is my amplitude. So whatever the energy you can consider, just give me values of A0 and A1. I can calculate all these functions here. series of functions. And it will not limit you. Remember, it will not limit you to the number of energy levels you can have, number of functions you can have, because it's a infinite series. Remember, it just goes on. That is also not what we want. Why? Because harmonic oscillator is constrained quantity, constrained system. For a given substrate and for a given hydrogen atom, for example, it will have limited number of energy levels. If you supply more and more energy, it can actually come out. For example, hydrogen atom will not sit on the silicon surface at room temperature itself. If you want to have this system, the silicon versus hydrogen atom system as a harmonic oscillator, you need to go down in the temperature. So that means the kind of energy levels it can have as a harmonic oscillator are limited. Okay? KT is almost 25 milli-electron volts. So this energy is only 25 milli-electron volts. Beyond that energy, this hydrogen atom dissociates itself from the silicon atom. So there is no harmonic oscillator. That means you do not need to consider energy levels beyond that particular value. Similarly, if at all it is a ball and a spring system, for example, there is a limit to which you can expand it, expand the spring. Beyond certain limit, it will break, the spring will break. So that means all those energies what you define, or all those wave functions you define, should be only up to that breaking point. So that means defining this A in terms of an infinite series will not give us a valid solution or a satisfying solution. Okay? You understand? Hydrogen and the hydrogen bonded to silicon, for example, it's a harmonic oscillator system. You can dissolve this hydrogen atom at room temperature. That means the idea of silicon and SiH as a harmonic oscillator system is valid only at low temperatures. That means it will have certain energy, right? So the limit of energy may be room temperature, for example. That means you are allowed to have only certain wave functions, or you are allowed to have only certain number of energy levels. You can consider any harmonic oscillator for that matter. The number of wave functions or number of energy levels are restricted. So that means assigning this function in terms of a series will not give us a valid solution. Okay? So what we do is the series solutions will give us wrong result, because it actually tells you that you can have infinite number of A's. I just give you values of A0 and A1. You can find out infinite numbers of A's that corresponds to infinite number of functions, infinite number of probabilities. That is not possible, right? Just for certain energy values of hydrogen atom adsorbed on the silicon, you can have the energies or functions. After room temperature, for example, you do not have a hydrogen atom there. So there is no harmonic oscillator. So that means the allowed values are limited depending on the system you have. So what we do is, instead of writing a series or A's in terms of a series, what we write is the polynomials. Okay? This also tells you that you have to stop the A values at certain number, right? You do not have a harmonic oscillator system beyond room temperature, means you have to stop these A's at certain value. And you substitute these values, you will get various functions, and after certain energy level, this dissolves. There is no harmonic oscillator, so explaining the wave function doesn't mean anything beyond that value of energy. Okay, so that means this series has to truncate or has to break at certain values of A in a real system. Okay, so that is why we write this in terms of some polynomials. Okay, And please again go through the lecture note, and I will just skip few steps from here. And these numbers are limited by, you can truncate these A's, various values of A, depending on what value of lambda you have here. Okay, I said for a given value of n or lambda, you have series of A's, but you can't have infinite A's. Okay, so the only way you can do is you select some number of lambda or some value of lambda so that this becomes 0. If aj plus 2 becomes 0, that means aj4 also becomes 0, or a4 also becomes 0. If a4 becomes 0, a6 becomes 0. So beyond certain level, all the a's become 0. That means you are limited only to a0 and a1. That means you are defining a proper harmonic oscillator system. Okay, so the polynomials depend on what value of lambda you select. Okay, for example, you select lambda as, give me some number. Lambda is 2e by h cross omega. I just select randomly some number, let's say 5. Okay, lambda is 5. For lambda as 5, what are the values of aj you can have? For j equal to 0, what will you get? For j equal to 0, you will have a2, this is 0, this is 1 minus lambda, or 1 minus 5, it will still be non-zero, right? So j is okay. What is 1 giving you? 1 is 3 minus 5, still it is non-zero. Okay, so what happens if you put j equal to 2? So this is 3, no, this is 5 minus lambda is 5, so that means this becomes 0. That means my j is 2, 2 plus 2, a4 is 0. If a4 becomes 0, then obviously a4 plus 2 should also become 0. If a6 becomes 0, a8 also becomes 0. So obviously all these numbers will become 0. So that means you are restricted only for 0, 1. 2 becomes already 0. Okay? Okay, you select, for example, lambda as 9. What are the values you can select? You can also select 0. J is 0, right? So lambda is 9. Okay, let me write down that. Aj plus 2 is 2j plus 1 minus lambda divided by j plus 2 times j plus 1. Now you just substitute and tell when do you have this 0. So this is for 4, j equal to 4, this becomes 0. So that means for all the values of aj beyond 4, this is 0. So only what you have is a0 plus a1u plus a2u square plus a3u cube plus a4u to the power 4. Only these values can satisfy this function. Beyond that 4 value, everything becomes 0. Remember. Okay. Similarly, you can select all these numbers for lambdas. Okay. For various values of lambda, you can select, and you will get various values of limited number of j's and limited number of a's and correspondingly limited number of functions. Okay. Now in general, this lambda can be written as 2n plus 1 for n equal to 0, 1, 2, etc. Remember, this 0 is different compared to these zeros here. Okay. This series lambdas in general can be written as 2n plus 1. Okay. For 2n plus 1, for a given values of 0 and 1, 2, you have a valid solutions. Okay. So then I already know that it is 2e divided by h cross omega. So I'll calculate 2e divided by h cross omega is 2n plus 1 for n equal to 0, 1, 2, etc. Or E is h cross omega divided by 2 times 2n plus 1, or you can also write h cross omega n plus half. Is it okay? Yes. So this is my energies. So this harmonic oscillator, which I considered having various amplitudes, okay? Remember, initially we started with thinking that the amplitude is very, very large. So that is why I got this solution. And now I want to use this function as a solution for all the values of amplitudes. Okay? The way in which you do is write down this as a series, because if you put this constant, it is only valid for large values of. If you put this series, you'll end up getting into trouble because there are infinite numbers or infinite coefficients. Infinite coefficient corresponds to infinite values of wave function. Infinite values of wave function correspond to infinite values of probabilities. But this is a harmonic oscillator, it is not a free particle. Okay? So you have to restrict somehow this series at some number. Okay? And that number depends on what sort of oscillator you have. And that is why replace this A by some polynomials. And this polynomial is related by this 2n plus 1 relation. And correspondingly, you get this value of energies for n equal to 0, 1, 2, etc. So how do you update this potential energy? You have discrete values, remember. The minimum energy is for n equal to 0, which is half of h cross omega. The next is for 1, which is 1 plus half is 3 times or 3 halves of h cross omega, so on and so forth. Okay. So while the classical ideas, we had continuous energies for all the values of x, half kx square, for example. So if you consider this harmonic oscillator, I hope this is symmetric. This is x, this is my energy. And for the classical system, u was half kx square, which is continuous values of energy possible, while now you have discrete energy values with E minimum as half h cross omega for n equal to 0. So that means the minimum energy level, do I have red pen here? Okay, let me see. The minimum energy you can have is half h cross omega. So this is my half h cross omega. The next energy level is for 3 by 2. 3 by 2 h cross omega, and 5 by E2 is 5 by 2 h cross omega. So this is E1, this is E0. Okay. E0 not equal to 0, you already had it in a particle in a box, remember. Particle confined to a infinite potential. There also you had E not equal to 0. E not equal to 0, En was n square pi square h bar square divided by 2m a square. A is the extent to which this particle is allowed to move around. This is A, this is infinite. Here also the minimum energy was not 0, remember. Okay. N equal to 1 corresponds to pi square. E minimum was pi square h bar square divided by 2m a square. While A is constant here, while A here is not a constant, remember, it is actually the amplitude of oscillations. Okay, so you can also write this as half k A square, for example. Okay, as and when this oscillates with the larger and larger amplitude, the energy also increases quadratically. While here, this energy levels are well placed, E1 or E0, E0, and this is 2 square is 4 times E1. I'll write this as E1, and then this will be 9 times E1, etc., etc. Okay. So similarly here, you have the discrete energy values, but here you have energy levels are not placed at the same distance along the energy axis. For example, this difference is 3 times E1, this difference is 8 times E1, or this is 5 times E1, and so on and so forth. These are not equidistant energy levels along the energy axis, while here you have equidistant energy levels. So that means if you consider a silicon surface and a hydrogen atom oscillating across the equilibrium position, for example, this system defines an equally spaced energy levels, and you can measure them. You can actually do this measurement of measuring the energy levels of this system. That means this hydrogen atom adsorbed at the on the silicon surface, and you can really get the energy versus the voltage, for example, or current versus voltage. You can determine, and you can determine the energy values. Okay, and you will see that they are equally spaced. And once you go beyond certain values of energy, in the experimental point of view, it is actually applied voltage. Once you go certain voltage, this will dissolve. So there is no harmonic oscillator field. Okay. So overall, what you found was that the energies are discrete, h cross omega. This is n plus half. Okay, En. While your classical ideas, so this is Newtonian world. I would say Newtonian world, and this is quantum world. You can apply to the classical system also the rules of quantum mechanics. The only difference is that this difference is very, very small. It's not measurable. Okay. There are always people ask, can you apply the quantum rules for macroscopic systems or bulk systems? You can apply. The only thing is that whether you can measure these differences. You are not able to measure differences. Okay, that's why we say that the energy levels are quasi-continuous in the classical scenario, while in the case of small world or case of a small system, these energy levels are widespread, so you can really measure using spectroscopy. Okay, this particular spectroscopy is the vibrational spectroscopy you measure. Okay. Now, this is using the differential equations, Schrodinger style of harmonic oscillator. There is one more way to do this using the operators. Okay. How would we do this? It's a simpler analysis of harmonic oscillator compared to various simplifications of the differential equations and the substitution and assumption, etc., etc. The operator methods are rather easy, okay, but you will end up getting the same result, okay, the discrete values of energy. Again, the starting point is same, the Schrodinger equation. Okay, so 2m del square psi by del x square plus v of x psi equal to E psi. This is my starting point always. You write down the Schrodinger equation and you have two parts in that. One is the kinetic energy, one is the potential energy, which is the sum of the potential energy and kinetic energy giving you the total energy. Okay. Initially you had written this as the sum of p square by 2m plus the kinetic energy, which is given as the total energy. That's my classical way of writing the total energy as sum of the kinetic energy plus the potential energy as the total energy. Okay. The difference what we did was, instead of writing the kinetic energy as p square by 2m, we wrote the operator form of the p, momentum. We wrote the operator form of the x. Okay. In this case of the harmonic oscillator, we have v as half k x square. K is related to the mass of the object, as k by m will give you the velocity or angular frequency, right? So you can just substitute here. That's why I'm saying this can be written as an equation with the momentum operator and the position operator. Okay. So what does this give you? Minus h bar square divided by 2m del square psi by del x square plus half kx square psi. K is square root of, square root of k by m is the omega. So k is m omega square. I can substitute here. Okay. So this will be m omega square and x square psi equal to E psi. Okay. Now, since we are discussing the harmonic oscillator, obviously the potential energy is half kx square. So the difference here is that you have the momentum operator here, p square by 2m. So you have 2m. So remaining is p square operator. Okay. We have discussed this initially. And then you have a x operator here. Okay. So instead of writing like this, what you can write as p operator plus m square omega square x square operator on psi as my E psi. Okay, I just get this half m into the equation, and you will get m square m to the power 2 omega square x square. So this equation now is in terms of x and p operators, rather than just the multiplication of x and momentum, or rather than using it as momentum and position. This is in the form of p and x with x comma p is I h cross. These operators have to satisfy this condition. That means the momentum and the position cannot be simultaneously measured to an arbitrary precision. Okay. So you write the classical Schrodinger equation. When I say classical, it is really using momentum and energy, and then substitute the p operator and the position operator. Okay. And then you by default consider this equation. Okay. So it should be valid. No, I'm taking 2m outside here, and because what is p operator? P operator is minus IH cross del by del x, right? So if you want to have this p square separately, you have to multiply by 2m, here. The 2 gets cancelled, so you'll get m square omega square x square. Sorry? Here, 2m e by, sorry. Okay. Okay. What did I do? I just took this 2m outside, so you'll get minus del square minus h bar square del square psi by del x square plus half, no, this is m square omega square x square psi, yes, psi equal to E psi. Okay. I just took 2m outside. Okay. So you can write this as p square plus m omega x square psi is 2m e psi, right? I just can write this m square omega square x square as m omega x square times psi operated on psi, giving you the energy. Oh yes, p square. So instead of writing this cap, I'll just write p square. That means we know that this is an operator, this is also an operator. Okay. What is this? This is a square plus b square. So I can write a square plus b square, or let's say x square plus y square is x plus iy times x minus iy. Okay, this is x square, this is y square. So that means the general solution, what you get is